Today we're going to learn about tectonic plates and plate margins. So here you've got a world plate map, and there's quite a number of different plates, and they've got these different names. A lot of them are kind of named after the continents or the major oceans. You've got the Pacific plate, North American plate, South American, African, and so on. You've also got this key here which shows the different plate margins, and we also have these arrows all over the map, and these arrows show the direction in which the plates are moving. So for example here they're moving apart from each other, so the Eurasian plate is moving apart from the North American plate. So what actually is a plate? What's the definition of a plate? Well, a plate can be defined as a section of the Earth's crust that floats on top of the mantle and moves slowly due to convection currents in the mantle. Okay? So what we're going to do is go through each of these plate margins in more detail. We're going to draw diagrams, so cross-section diagrams for each one, and explain the kind of processes and landforms at each of these plate margins. So let's start with constructive. So constructive. So the first thing I'm going to do is I'm going to draw, so these are all going to be cross-section diagrams, apart from one of them, but all the others are going to be cross-section diagrams. It's only the conservative that we're actually going to do like a bird's eye view diagram. You'll see why later. So constructive. The first thing I'm going to draw is my crust. So remember, these are simple cross sections. That's all you need. So constructive, we're going to draw one of the plates here. Remember, plates are sections of crust. So that's one of my plates, one of my sections of crust. And then I'm going to draw the other one as well, just opposite like that. And these plates are moving apart, so I'm going to draw in my arrows to show that they're moving apart. So remember, constructive, so all the green boundaries here on the map, the green, remember these arrows here are showing that these plates are actually moving apart. So the constructive margins, you'll notice all of them, the plates are actually moving apart. So I've left a bit of a gap there because the plates are moving apart. It's a little bit of a gap where the magma will rise through that gap. You'll see in a second. So before that, I want to draw in the ocean surface. So I'm gonna just draw that in because most constructive margins actually occur underneath the ocean. So I'm going to draw that in. And now I'm going to draw in my arrow showing the magma rising. So it rises through the gap like that. And I'm also going to draw in my convection currents within the mantle. And they're going to be going this way. So like that. So the same direction the plate's moving, and they're going down like this, and eventually that way, where the magma will then eventually rise through that gap. And on the other side, I'm going to do the same thing. So it's like a mirror image on the opposite side. It's like a mirror image. So these are my convection currents. Now I'm going to add some labels. So first of all, convection current, this as well. We've got the mantle, because don't forget convection currents are found in the mantle. Now here, the rising magma, there's actually a term for that rising of the magma through the gap. It's called upwelling. Upwelling of magma. Upwelling basically means rising. So let's put it in brackets there, rising of magma through the gap between the two plates. Okay. Then I'm going to label my plates. So first, the crust type. Now this is oceanic crust because it's under the ocean. This as well. And I'm going to put in plate examples as well, plate name examples. So if we go back to our plate map, you'll see that there's a few examples we can choose from. I usually go with one of these, so the Eurasian plate and North American plate. So we're going to label that in. So we've got the Eurasian plate and the North American plate. All right. And then I'm also going to label my ocean surface as well. Okay. And what we need to do now is we just need to label the landforms. So this is where you're going to have a certain landform. Now the landform is called a mid-oceanic ridge. And an example of that is the Mid-Atlantic Ridge, which you might have heard of before. The Mid-Atlantic Ridge. Now you also get volcanoes here. We're going to look at the different types of volcanoes in more detail later, but you basically get two types of volcanoes here, shield and fissure volcanoes. I'm just going to add that in as well. Shield and fissure volcanoes occur here. And now that diagram is completed, fully labeled. So what we're going to do now is we're just going to add some bullet point processes. So I've left this gap here for a reason. We're just going to add some bullet point processes here, just to outline the geographic processes that are happening at this plate margin. So first of all, you'd want to start with the plate motion. So what direction the plates are moving at. So here, plates move apart from each other in opposite directions. That's the first thing. Then we can start talking about this magma rising to fill that space there. So as the plates are moving apart, you've got, remember, that upwelling of magma filling the gap. So we can say magma from the mantle rises through the gap between the two plates in a process called upwelling. Now, as soon as that magma comes into contact with the seawater here, which is relatively cold, it's going to cool and solidify very rapidly. Okay, so magma cools and solidifies rapidly once it comes into contact with seawater. Okay. This creates new ocean floor and the landforms found at constructive plate boundaries, plate margins, which is your mid-oceanic ridge and shield volcanoes, and also fissure volcanoes. Okay. And that's all you'd have to say in terms of the processes. Now, of course, you could go into more detail and talk, a little bit about earthquake characteristics and some of the volcano characteristics as well at this plate margin. We could add, so in terms of earthquakes, you do get earthquakes happening, but they're quite low magnitude and shallow focus. Okay. Low magnitude and shallow focus. Shallow focus means they're quite close to the surface. Quite close to the surface. Low magnitude means they're relatively weak, so they're not very strong. Now, the reason that is because the earthquakes are actually only formed due to the heat from the rising magma. It's not really any kind of friction between the plates here. There's no rock really getting stuck. There's no kind of buildup of pressure from from the friction between the plates and between rocks sliding past each other. It's only because of magma rising, the heat from the magma rising. Think of it as kind of like boiling a kettle. Once the kettle starts to really boil, if you look closely, you can kind of see it vibrate and you can like hear it as well. It's kind of like that. So that concludes the constructive margin diagram. The next one we're going to do is destructive. So always give your diagrams titles and fully labeled, annotated. It's really important they're very clear. So here again, it's going to be a cross section, nice and simple. The first thing I'm going to do again is draw my plates. So here we have one of the plates. It goes down like that. And then here we have the other plate like this. I'm going to draw in my ocean surface again, which is here. So this is land here. And I'm going to draw in my convection currents as well. So we've got one here going like that, this way. Got one here as well going this way. I've left a bit of space here for a reason, you'll see in a second. I'm going to draw in my arrows. So this time the plates are moving towards each other, but this one is actually going underneath the other one. And this is called subduction. So this plate is actually subducting underneath this one here. Now we're going to add more labels in a second. I'm just going to draw in the landforms over here. Okay, let's add some labels. So first of all, we've got our crust type. Now this is continental crust. This is oceanic, because it's under the ocean, this one. This is land. Plates are moving towards each other. So we go back to our map. So the red with the kind of triangles, that's destructive margin in the key there. So there's a few of them. I tend to use this one here as an example. So what's happening here is the Nazca plate is basically subducting. So that's your oceanic crust. That's subducting under the South American plate over here. So I'm going to use those plates as the examples. So this one we've got South American plate. And this one we have the Nazca plate. So why is the Nazca plate subducting underneath the South American plate? Because oceanic crust is denser than continental crust. It's denser, it means it's heavier, it will go underneath. I've drawn in convection currents again, so we're going to label those. Here as well. And this is the mantle. All of this down here is the mantle. And you do have lava rising, and it rises just over here. I'm going to draw it all the way up. Now if you wanted to get really fancy, you could actually draw in, so this is a volcano, it's a composite volcano. More on those later, but you could get really fancy here and actually draw in a little magma chamber, which is just kind of a accumulation of magma just below these composite volcanoes. Composite volcanoes are another type of volcano along with shield. Okay. I'm going to label this again as magma rising. Whoops. Magma rising. So the landforms, well, the landform is basically a chain of mountains. They're volcanic composite volcanoes. So we're going to label that as well. Chain of volcanic mountains with composite volcanoes. We'll have a look at the different volcano types and their characteristics in a later lesson. So don't worry too much about that for now. I'm going to label my ocean surface again over here. And then there's a few more things to label. So there's a certain zone which is round about here. And this is quite important. This is called the subduction zone. So this is where that oceanic plate subducts underneath the continental plate. And the final thing I'm going to label is just above the subduction zone, right here, you have a very deep part of the ocean. This is a deep sea trench. An example of that, you might have heard of this before, is the Marianas Trench. It's the deepest point on Earth, very deep. Think of it as almost like a kind of an underwater canyon going down. It's really, really deep. So now let's just check we've got all our labels. Yep, that looks fine. So what happens here is, we could add this in as like an annotation, is the subducting plate starts to melt and disintegrate, and this is part of the reason why you've got the magma rising here. So I'm just going to add in one final label. So melting plate disintegrates back into the mantle. So as this plate here melts, you have loads of gases released, water vapor from a bit of seawater within the plate, also carbon dioxide, and this actually mixes with the surrounding magma, causing it to become less dense and therefore rise up. Now, along with that, you've also got some displacement of magma here, due to that plate moving downwards. That also helps to push up that magma as well, but it is mainly the gases being released. So as the magma rises up, it will form these mountains. They're volcanic. These will build up as the volcanoes erupt over time. You do also have a little bit of compression since the plates are moving towards each other, also helping to build up these mountain chains here as well. Okay, now we're just going to add some bullet points again. So same like the previous diagram, start with the direction the plates are moving. Oh, by the way, one more thing to add. The volcanic mountain chain formed here, some of you may know, is called the Andes. It's the second largest or second longest mountain chain in the world after the Himalayas, called the Andes Mountains, and they're very much volcanic. So I could just quickly add that in here actually. So for example, the Andes. Always good to have examples of landforms and plates as well. Right, so some bullet points. So first of all, we're going to start with the plate movement again. So plates move towards each other, and the denser oceanic plate subducts underneath the less dense continental. Okay. Then we talk about the melting process and then eventually the magma rising. So the subducted plate eventually melts and disintegrates back into the mantle, releasing gases such as carbon dioxide and water vapor. These mix with the surrounding magma, causing it to become less dense and therefore rise. Okay. This forms a volcanic mountain chain over time, and remember the compression helps with that as well. Okay, and these include composite volcanoes. And in terms of earthquakes, so remember here our last bullet point was all about the earthquakes. Now here you also get earthquakes, but they're much stronger in magnitude because you have loads of friction between the two plates due to the subduction. So you will get earthquakes happening along this subduction zone. So here, here, so where there's the highest amount of friction, you will get earthquakes happening. I'm just going to add in a little key here. A red X means earthquake activity. So the final bullet point is going to be about the earthquakes. So high magnitude, deep focus earthquakes occur at destructive plate margins. Remember, deep focus means they're quite deep underground compared to earthquakes at constructive plate margins. Okay, now the next one, so this one was kind of the most complicated one out of all of the plate margins, destructive. The next one we're going to do is conservative. Now this one's much simpler. Now I mentioned earlier I was going to do one as a bird's eye view diagram. This is it. This one's quite simple. All we're going to do here is we're going to have our two plates like this next to each other as a bird's eye view diagram, and then we're going to draw in our arrows. So you've got one going this way, the other one going this way, and we're going to do a key again as well for possible earthquakes. So earthquakes could happen anywhere along here where those two plates meet. So if we go back to our plate map, conservative is blue. Now there's only one really drawn in here, which is this one, which is the kind of main one that you need to worry about. This is the San Andreas fault, basically. The North American plate and the Pacific plate move alongside each other here. They move alongside each other. Both are continental, so we're going to add some labels here. So we've got continental crust. Oops. Continental crust, and here as well, continental crust. Plate examples, we're going to do Pacific plate and North American plate. And the landform, which would be all along here, is the San Andreas fault. San Andreas fault. Some really cool pictures of the San Andreas fault on Google, if you have a look. And so that's all we really need for this one. Like I said, it's much simpler. In terms of bullet points, we're going to again start off with direction of plate movement. So plates move alongside each other. That's the key thing, alongside each other. Now they can either move in opposite directions, which is what I've drawn on the diagram here, or in some cases they can also move in the same direction. However, if they move in the same direction, they have to move at different speeds, because otherwise you wouldn't have any friction, you wouldn't have any earthquakes. So either in opposite directions or in the same direction but at different speeds, as otherwise there would be no friction and pressure build-up, and therefore no earthquakes. It would be it would be extremely unlikely for them to actually be moving at exactly the same speed anyway. Right, so let's talk about earthquakes. So strong, or let's say high magnitude intermediate to deep focus, kind of a range here, earthquakes occur at conservative plate margins. Again, this is due to a lot of friction between the plates, pressure buildup, and then the sudden release of that pressure is what an earthquake is. So like in our destructive boundary, you have a lot of friction and pressure buildup where the two plates meet along here, along that subduction zone. Now, the only other thing we're going to add here is that there's actually no volcanoes present at conservative plate margins due to no source of rising magma. There's no magma rising here, so there's no volcanic activity, only earthquakes. Okay, and the last one we're going to do is Continental Collision plate margin. Again, this is simpler. So here I'm going to do a cross section again, and this time I'm going to do it like that, and then this line separating my two plates. Now notice I've done these plates a lot thicker than these ones. That's because these are continental crust, and continental crust is thicker than oceanic crust. So let's label that continental crust. So as the name suggests, it's collision between two continental plates. I'm just going to draw in my convection currents. Convection currents are really important in driving plate movement. It's the main reason why plates move. It's due to these convection currents in the mantle. Do another one here as well, like a mirror image. Now there's no rising magma here, so there's no volcanoes. But we are going to label plate examples. So if we go back to our plate map, continental collision is the orange, so there's one here, and it continues all the way here as well. So I tend to use this example, which is definitely the best one. Collision between the Eurasian plate and the Indo-Australian plate. And this produces the Himalayas, the Himalayan mountain range. So let's label that. So we've got the Eurasian plate colliding with the Indo-Australian plate. And I'm going to put in our arrows again to show the plate movement. And in terms of landforms, we have very tall fold mountains, but they're not volcanic. There's very tall mountain chains called fold mountains. The example is the Himalayas. Okay. And that's all we really need to label there. So you can probably imagine that because of this collision of the two continental plates, it results in these mountains forming due to the compression. Now you can get earthquakes, and they can be quite strong. So let's add some bullet points. Again, we'll start with the direction of plate movement and end with the earthquake activity. So plates move towards each other and collide. Okay, this results in compression forming tall mountain chains called fold mountains. No volcanoes are present. However, we do have strong, keep saying strong, high magnitude, it's a better term to use, high magnitude, deep focus earthquakes. And again, that's done. So those are the 4 plate margins.